Hello. Purpose of today's video is to explore some of the way that IB tends to ask questions about use of Poisson distributions. So, as you recall from class, a Poisson distribution is a probability distribution based on events that are relatively unusual, like snow days in a school year or a number of people walking by a doorway during class time. Or, take an example like this one, we have somebody who manufactures wire and is looking for flaws. Basically, we have to make some assumptions. One, that this is a Poisson distribution because it doesn't say so specifically. But number two, the part where they say there's an average of 1.8 flaws per meter in the wire, that's a clue that it's going to be a Poisson distribution as well, because the only information you're given is that there's an average of 1.8 flaws per meter. The assumption then is that we're going to have infinity meters, and we can figure out on average that there's going to be 1.8 flaws for each meter within those infinity meters. Anyway, that gives us the possibility to determine these two kinds of questions. The first one is really straightforward application of the Poisson distribution formula, which is written for you here, and it's just asking what's the probability that you're going to find exactly one flaw in exactly 1 meter of wire. So this follows a Poisson distribution with a mean of 1.8, and because we're only using 1 meter and there is an average of 1.8 flaws per meter, we can put in 1.8 as our number. So that's going to be 1.8 to the 1 power, because we're looking for 1 flaw, and e to the negative 1.8 over 1 factorial. Remember the proof of this we talked about in class. This turns out to be, to 3 sig figs, 0.298. So there's about a 30% chance that this guy's going to find a flaw in 1 meter of wire. Which makes sense because they find a flaw in 1.8 meters of wire, so 1 meter could be clean, but it could have some sort of flaw in it somewhere. So the next question shows some of the subtle variations that are used in reference to Poisson distributions. At least is something we've seen before, and here what they do is they actually increase the number of meters that the guy is inspecting. So what we have to do is we have to make a modification of our mean. It's 1.8 flaws per meter, so over 2 meters we would expect 3.6 flaws. So we have to use 3.6 in our Poisson distribution, otherwise we're going to be messed up. So the probability of it having at least 1 flaw within a 2 meter length of wire is going to be the same as the 100% probability less the probability of no flaws. So if we have no flaws within 2 meters of wire, we take away that from 1, we'll have the probability of having at least 1 flaw. That's 1 or more. So just the simple calculations. Now, both of these can be backed up with the calculator. Once again, the notes are followed in class and everything else, so I'm assuming you should know how to do that, but this is just the basics for how to set up this simple formula. Things get a little bit more interesting when we start getting into the more IB high-level style questions. And a lot of times, even with those high-level problems, you'll get parts that are just really straightforward, and then they'll give you a nice little gut punch at the end, and that's what's going on here. You see, we have a car company. They've got 2 limousines, not 1, and they rent them out. They say hire in other countries. We say rent. And the number of requests per day has a Poisson distribution. It was nice of them to say so, with a mean of 1.3 requests per day. So on any given day, you'll have about 1, maybe a little more people asking to rent a limo. Find the probability that neither limousine is hired. Now, the problem, of course, is they did say Poisson up here, but they didn't specify that they meant in 1 day, but we have to assume that's what they meant. So we're assuming in 1 day, an average of 1.3 rentals per day, anticipate about 27% chance that nobody's going to be renting your car. You only have 2 of them. Part B says find the probability that some requests have to be denied. In order for that to happen, we need to have 3 or more requests. The first 2 get the car, and anybody after 3 has to, find a way to walk, I guess. So, all we have to do there, since it's an at least situation, we take the 100%, and then we subtract the cumulative probability from 0 to 2. So the chance of having the no cars or 1 car or 2 cars rented out, these are all the ways that nobody gets turned away. Subtract that from 1 and you get the probability that somebody, at least 1 person, is being turned away. And that's a 14.3% chance. Again, all straightforward, but we get to the last question, and it says, if each limousine is to be equally used, that is to say they don't have one they favor over the other, how many days in a period of 365 days would you expect a particular limousine to be in use, one or the other? So in other words, in 365 days, pick limousine A. How many days would you expect limousine A to be rented out? This is a little tricky because it involves using probability distribution in conjunction with a Poisson probability distribution. So there's two different distributions going on here. One of them has to do with the probability of the company renting out a car on a particular day, and the other has to do with the probability of a car being rented out over a year. So there's subtle variation here, but nonetheless, we're going to redefine our variable. We have a new discrete variable, which is in this case y, and y represents the number of limos rented in one day. So these are the different things that can happen. We could have no rentals, one rental, or, and this is the tricky part, two or more requests. So it's kind of like, it's a little bit of a tricky little animal here, and basically we could say, I'll explain it as we go, and this will make more sense, trust me. For part A, we already answered the probability of none of the limos being rented out. One of the limos could be rented out by working out a little Poisson for one, and we get about a 35.4% chance, and then we can basically say that the cars will be rented out as long as there's not one car or zero cars. So to get the probability for the last slot, we do not do a Poisson on two, we do a cumulative at least situation. So two or more rentals is the way to get all other or all else sorted out. And it should make sense when you just look at it. There's only three possible things that could happen: zero rentals, one rental, or the other. And so basically if we add these up and subtract from one, we'll have all the other covered in one shot. Anyway, what do we do with this information? Well, using some logic, I can read this and say about 37% of the days in the year, so about a third of the year, both cars will go. So that means in 1/3, we're definitely going to have one of those limousines hired out. 35% of the days, only one car is going to be rented out. And here's where it gets a little hairy. It says one half, well, not it says, I said, one half of those belong to the other car. In other words, it says up here that the limousines are to be equally used. So one of these 35% of these days is going to go to my car, and the other it's going to go to the other car. And so we get half of the chances for one car rental only, plus we get all of the chances for two car rentals. So we simply add that up. We get the probability of two or more requests, and we also get the probability of y equals 1. But we're going to take half of that probability, add it all together, and we get around 55%. Now, to answer the question, I simply say that we're going to have the probability of having one car rented times 365 days in a year is going to give us approximately 201 days in the course of a year where one limousine should be rented, which is not bad in a business that has two cars. To expect that, 2 out of 365 or 200 out of 365 days, one of your cars at least is going to be used. That sounds like a good business model. So that's about it. Thanks for watching. Sorry it went a little long.